Hello, everyone. Welcome back to Thermodynamics and Kinetics, CH430A. In this video, I am going to start talking about a math topic known as partial derivatives. And I'm starting here in our new unit of thermodynamics. So we've left statistical mechanics and we're moving into thermodynamics. I'm going to start with this math topic because this is a topic that and a skill that we are going to use throughout the this entire section of thermodynamics. Okay, so up until this point, we have been working with probabilities, distributions, and fractions of a system in a particular state. With this, we used a lot of integrals and a lot of summations. But now we are moving into thermodynamics, and thermodynamics is largely focused around change. And so to understand how things change with respect to a variable, we have to use a derivative. So to start us off, I'm going to talk through some of the basic rules of derivatives. These three really are the chain rule, the product rule, and the quotient rule. And let's start with the chain rule. The chain rule is for whenever we have a function that is a function of a different function. And so to take the derivative of this, we have to take the derivative of the what's called the inner function. The outer function is in yellow, and we multiply it times the derivative of the inner function. So just to make sure, yellow is what we are going to call outer, and red is what we are going to call inner. And so let's do an example. In this example, this 5 minus 6x, this is my inner function. This raised to the power of 5 is my outer function. So to take the derivative of this, the first thing I'm going to do is take the derivative of the outer function. And to take the derivative, we move the exponent down in front, and it's times what is in the middle, raised to the exponent minus 1. That is my f primed of g of x. So this is my outer function. But now I also have to take the derivative of the inner function, which is going to be minus 6. And so if I simplify this, I get negative 30 times 5 minus 6x to the 4th. Okay, so the next one is the product rule. And this is taking the derivative of two functions that are multiplied together. So I have one function f of x, and I have another function g of x. And what we do, my mnemonic for this is the first times the derivative of the second plus the second times the derivative of the first. Okay, so let's do an example. So I need the first times the derivative of the second. And we've got to be careful here because the derivative of the second uses the chain rule. So I have 3 times 5x minus 1 squared times 5 plus the second times the derivative of the first, which is 4x cubed. And then you would simplify this and make it look pretty and report your answer. Okay, so the last option is the quotient rule. It's the last special rule we have to think about. And this is whenever we have one function divided by another function. And this is the one that always confuses me. So this is a lot like the product rule, where we have the derivative of the first times the second minus, give you a decent color, minus the first times the derivative of the second. But this time we have to divide it by the denominator squared. So let's do an example. So if I were to take the derivative of If I were to take the derivative of 3x plus 9 divided by 2 minus x, I'm going to first take the derivative of the top, which is going to be 3, times the bottom, which is 2 minus x, minus the top, 3x plus 9, times the derivative of the bottom, which is negative 1, all divided by the bottom squared. Okay, so we're about to make derivatives more complicated, but these rules, these 3 main rules, are still going to apply. Okay, so partial derivatives. This is really what we start to think about if there are more than one variable. So the derivative of a function with respect to one variable while I hold the rest constant. The chain rule, product rule, and quotient rule still apply. So what am I saying? I'm saying that we have a function f of x, y, and z, and I'm going to take the derivative of that function with respect to x. And so this is with respect to. And I am going to hold my variables y and z constant. So hold these variables constant. So this means that when I'm taking the derivative of f of x, I really only have to treat x as a variable. Y and z are going to be constants and get treated the same way as the number 2 would if it showed up in an equation. Okay, so let's do some examples. So let's start with, I have my function f of xy equals x squared plus y squared. The derivative of f with respect to x is going to be equal to 2x because in this case, y is being held constant and the derivative of a constant is 0. Likewise, I can also take the partial derivative of f with respect to y, holding x constant, And in that case, my expression is going to be equal to 3y squared. So I can also do things like, and so now let's do another example. Let's rearrange PV equals nRT to P equals nRT over V. And let's take the partial derivative of P with respect to T, holding N and V constant, because R is always a constant. And so I like to rewrite this as P is equal to nR over V times T. Because in this case, my N and my V are constants, and so I isolate that. And so the partial derivative of P with respect to T, holding N and V constant, is equal to nR over V. I can also do the partial of P with respect to V, holding N and T constant. So here, I will say that P is equal to nRT times V minus 1, because I don't like the quotient rule, so I rearrange so that I don't have to do it. And I would get that the derivative is equal to negative nRT V to the minus 2. Okay, so I hope that this gives you some ideas on how partial derivatives work with some examples. We're going to be using this a lot throughout the next 5 weeks. So I'm not going to give you a now try this right now. Instead, after the videos on Wednesday, whenever we have examples with thermodynamics to be able to use, I'm going to give you a now try this that applies these concepts of partial derivatives with thermodynamics.